So our speaker today is Allison Valji. I'm not sure if I'm pronouncing that correctly.
That's right.
Allison, okay, great. Thank you. Allison is our winner of the Charlie Hammond Award. I think everybody by now knows what the Charlie Hammond Award is awarded for. We had one winner this year. Typically in a year we'll have two winners, but this year we only had the one winner. So congratulations, Allison. This is directly from the write-up that Allison sent us, a research project on confirming exoplanet candidates using transit photometry and searching for multi-planetary systems using transit timing variations. Very timely. It's a very current science happening right now. Very current citizen science happening right now. So that's perfect. Elson, I'm going to go ahead and stop sharing. This is where it's all yours.
Hey, just a couple of note takings for the rest of you. Please put yourselves on mute. And Allison has asked that you hold your questions to the end, although you can send them to me in the chat if there's something really jumping that needs to be repeated. I'll ask.
Okay, Allison.
Okay, let me just share my screen. Okay. Like I said, I'm Allison, and I go to Darien High School, and this is my project confirming test exoplanet candidates and searching for multi-planetary systems using transit photometry and timing variations. Okay. And to kind of begin, I really got into astronomy just kind of as a child, just looking up the stars and pointing out the constellations. But I really learned a lot more about it during my time in high school. My school has a like 3-year science research class where at the beginning and sophomore year, students perform a lot of bibliographic research on a topic of their choosing. And then eventually they try and find a mentor to conduct an independent research project. And I focused mine a lot on exoplanets and particularly using the transit method. Um, my mentor is Dr. Don McCarthy. He's a retired professor from the University of Arizona, and he also runs a summer program for high schoolers called Astronomy Camp, which basically just like invites a bunch of high school students to Mount Lemmon in the observatory there to use the telescopes and learn how to use them and just kind of learn about astronomy for a week. And he is the director of this program. And after I attended this program, I kind of reached out to him to see if he would kind of help me out with my project. And he helped me conduct my observations and collect my data so that I could do this project. Um, so I really kind of zoned in on exoplanets like pretty early on in sophomore year, mainly because I just thought it was so cool that there are kind of planets outside our solar system with all these different conditions and stuff. So this project kind of focuses all on that. Um, and it particularly uses the transit method, which is when a planet passes between the star it's orbiting around and the observer on Earth, and that it blocks a portion of the brightness. And in doing so, the brightness of the star will decrease. Um, and this can be displayed on a brightness over time graph called a light curve, where the brightness decreases when the planet is transiting. And then TESS, or the Transient Exoplanet Survey Satellite, is a space telescope designed for finding exoplanets using the transit method and kind of just finding as many as possible. But when they're found, these exoplanets are labeled as candidates because they're not confirmed to exist. Because when TESS observes a star and detects like decreases in brightness, um, they can sometimes, these exoplanet candidates can turn out to be false positives, meaning that the change in brightness is the result of something else, say a variable star or an eclipsing binary star. So there needs to be follow-up studies to confirm whether or not these exoplanet candidates exist. And these are called TOIs, or test objects of interest. So my project also looked at transit timing variations, which it happens when if there's like a second planet in the star system, that planet can gravitationally pull on the first, and this can cause the orbit to speed up, slow down, or change shape which means that the transit will happen earlier or later than predicted. And these variations in timing, if we see them on the light curves, can indicate that it's a multi-planetary system. And overall, my study focused on three different test objects of interest to confirm whether or not they exist. And it's these three. And the reason this study is so important is because it's kind of a first step before future research can be done. We need to find planets first before we can perform other studies like looking for planets that are habitable or looking at the architectures of multi-planetary systems. Because we're not really going to expend expensive resources on a planet that may or may not exist. So like I said before, like kind of the main question that my project was asking was, do test exoplanet candidates 2I3856, 2I1858, and 2I1832 exist? And are there any transit time variations present in the star systems? And what we have hypothesized is that exoplanet candidates 2I3856, 2I1858, and 2I1832 will be confirmed to exist, and there will be some transit time variations because the majority of test exoplanet candidates are confirmed, and many systems have some timing variations. So basically, because approximately 70% of candidates are confirmed, we expect that these ones will as well. And there are like a decent number of multi-planetary systems, so we expect to maybe see some timing variations. So the first thing we did before collecting our data is I went on this website called Swarthmore Transit Finder, which is put out by Swarthmore College, which basically is just like a database of all of information on all like both confirmed and candidate planets, kind of giving their name, when they're going to be transiting, their magnitude, the start time and end time of transit, the duration, star coordinates, all stuff like that. And what I got from this was I was able to choose three targets. We kind of based this on ones that were of a good magnitude for the telescope we're using, as well as ones that had decent enough transit depth where it would be detectable by a ground-based telescope. And also we wanted to look at kind of stars that had are exoplanet candidates where the orbital period is very short, so they transit frequently, meaning there'll be lots of dates where we can observe them, and also ones that are close to like kind of a whole number, so that we don't so it's actually transiting at night pretty frequently. And then once we chose the three targets, we were able to get the star coordinates in the form of right ascension and declination. So we know where to point the telescope, the time of transit, as well as some star charts, which look like this. And these star charts allow us to find the star in our images, because when we take an image, it looks something like this. And we want to be able to know which star is the one that we're trying to measure the brightness of. So these finder charts kind of help us do that. With the help of my mentor, I used the Phillips 24-inch telescope located on Mount Lemmon in Tucson, Arizona. And we were able to use the telescope remotely, so my mentor could log into the telescope from his computer, so that we didn't have to actually be on the mountain, because this was like in the spring of last year of 2024, so I was like in school and stuff. And we were able to collect our data that way. And then when we actually went to observe, after pointing the telescope at the star with using based on the coordinates, we would take like an initial test image and compare this manually to the finder charts to kind of see if the star we're looking for is in frame and we can find it. And then we'd also upload the image to astrometry.net, which is a website that allows us to determine the precise coordinates of the image, so that we can make any small adjustments by like a few arc seconds or so, if we need to make sure that the star is in frame and centered. And then we would take images using the based on like kind of automatically, because the telescope has automatic tracking, for the duration of the transit plus an hour before and after. So we have like some sort of pre and post transit brightness to compare to. And we observe with a red filter to filter out moonlight. And after kind of collecting the data, we also took some calibration frames in the form of darks, biases, and flats. And what these do is they allow us to reduce noise in the light curves. And these are kind of the dates that we observed on. We observed 2I3856 three times, and I'll kind of explain why when I go through the results. And this was all in 2024. After we took the images, I was able to use AstroImage to perform multi-aperture photometry, which basically allows us to measure the brightness of the star in each image and plot it on a brightness over time graph or a light curve. It also allows us to include the calibration frames to reduce noise. And then after we create the light curves, I could analyze them. Um, First, in terms of confirming whether or not the planet exists, I'm kind of looking for just one singular dip in brightness because say if it was like a variable star, we might see more of an oscillating pattern. So looking for that one singular dip, and then also looking for any timing variations, kind of comparing does the planet transit when we expect it to based on the predicted times from Swarthmore Transit Finder, or does it happen earlier or later? And then the final thing we did was we wanted to calculate planet radius um, based on our light curves. So what I did is I know that transit depth or the change in brightness is proportional to the ratio of planet area to star area. Um, so plugging in for pi r squared, I was able to derive this formula for planet radius, where the radius of the star comes from literature, an article that I read by Sasson et al. And then as well, the transit depth comes from our graphs themselves. And then because both stellar radius and transit depth has an error value, we wanted to account for this error, and I derived the formula for error propagation. Based on this general formula, which comes from another article I read, I was able to apply that to the equation on the previous slide to derive this formula, where sigma is the error value. So this is error on planet radius, which we're calculating, and then error on transit depth comes from our graphs. AstroImage calculates that for us, and then error on star radius again comes from literature. So this is the first graph. This is for 2i 1858. Just to kind of explain what we're looking at here. On the y-axis, we have brightness, and this is normalized to 1. So like 1 is the normal brightness of the star. And then if you drop down to 0.98, that's like a 2% decrease in brightness. On the x-axis is time. And then each kind of faint blue point is one image. And then the kind of darker blue points are 5 of those image binned or averaged together. And then the green line is a model fit that AstroImage plots through the curve for us. The dashed red lines are predicted times of ingress. Ingress is when the brightness starts to decrease, and egress when the brightness starts to return to its normal brightness. And these are predicted values from calculated from Swarthmore Transit Finder, so that we can then compare to when the actual ingress and egress is. And then finally, these points down here are the comparison stars. A comparison star is just another nearby star that's used to calculate a relative change in brightness. These are arbitrarily scaled and shifted down, but basically the reason they're there is just to make sure that they're flat and there's no strange fluctuations there. So for 2i 1858, I kind of see one singular dip in brightness, indicating that the planet we're looking for does exist, and I don't really see any timing variations. For TOI 1832, again, I kind of see the transit shape I'm looking for, um, indicating that this planet does exist. However, there are some time variations as you see this kind of starts and ends earlier than we expect, but there is kind of some noise around ingress and egress, meaning that the model fit may not be perfectly accurate. So this could be time variations, it also could not be. Also, the comparison stars do slightly slope, and we only have like kind of one night of observation, so we can't really say for certain that there are timing variations. But this would be a star system that maybe is worth observing more in the future to kind of see if there actually are timing variations, and also maybe performing some radial velocity measurements to really indicate if it's a multi-planetary system or not. But again, we can confirm the planet does exist. And then for 2i3856, we observed this star 3 times, and that's because we kind of saw some strange results. Here it's kind of like one large increase in brightness of about 4.5%. The expected transit depth or change in brightness was about 1.3%, so this is much larger than we expected. So whatever causing the change in brightness is a larger object than the planet we were looking for. But then on April 22nd, we observed it again, and we kind of see the predicted transit shape, one singular dip in brightness, and a transit depth of about 1.3%. So the planet that we're looking for is right here. It does exist. But for some reason, we couldn't see it in the observation 2 nights before. So then we observed it 2 nights later. And again, this time we see a decrease in brightness of about 4.5%, meaning that the larger object that we saw on the 20th is again here. And the reason we concluded that it's likely some unknown object, although we can't say for certain, is because we used the same comparison stars in all three ones, which would kind of mean if there was some sort of systematic error, then we would have probably seen it on the 22nd. So again, this is another star system where the planet we're looking for does exist. It's right here on the 22nd. But there's some larger object, possibly, that could have a larger or a different orbital period, which is why we only see it sometimes and we only see part of the transit. It also could be something else, but again, this is a star system that would be worth taking another look at. So overall, kind of the results summarized is we were able to confirm that all three candidates are confirmed to have exoplanets. And we did find two potential multiplanetary systems in the case where it's possible that there's time variations in 2I1832, and there is a possible larger unknown object in the 2I3856 system. But again, we do need more observations to kind of confirm any of this for certain. And we were able to calculate planet radii. Given that it's a ground-based telescope, and we couldn't really calculate to a really large number of significant figures, but we do have rough estimates on the planet radii given in Jupiter radii. To restate my hypothesis, the exoplanet candidates 2I3856, 2I1858, and 2I1832 will be confirmed to exist, and there will be some transit time variations because the majority of text exoplanet candidates are confirmed, and many systems have some timing variations. So this is supported because we did possibly see some time variations, and we were able to confirm the three candidates. Some sources of error is there was some noise in some light curves, particularly in some of the later ones. And this is probably the result of either atmospheric interference because it's a ground-based telescope or just noise at the detector itself. And we did try to kind of reduce some of this systematic noise with the comparison frame or the calibration frames, but it's not perfect. So if there's a lot of noise, that could impact the accuracy of the model fits that AstroImage-J produces for us. And again, the reason this is important is because once we confirm these planets, they can be added to a list of confirmed planets, and then there can be follow-up studies looking for habitability or orbital architecture. And kind of the reason I think exoplanet research is so cool and why we kind of need to be doing it is because by learning about these other systems and kind of seeing how they're different from our own, we can then compare that to our own solar system, which could give us insight into Earth and our solar system itself. As for future research, I definitely want to try and follow up on those two potential multiplanar systems to see if there actually is maybe an unknown object or if there actually are time variations. Um, if I can get more telescope time, I would like to do that. And then also kind of the next step would be doing radial velocity measurements. I don't really have access to a high quality spectrometer to do those, but that's something that would need to be done to kind of further confirm these planets as well as kind of answer some of these unknown questions that we had afterwards. I'd like to thank my mentor, Dr. Don McCarthy, as well as my teachers in school for all their help and support in this project. Do you guys have any questions?
Don't have any questions in the chat, Allison, but let me just say, first of all, wow, thank you. And second, to Bill Denayo and Scott Tracy, you chose the recipient of the Charles Hammond Memorial Award for Excellence in Astronomy for the Astronomical Society. Very, very well. I just finished attending a seminar on Exoplanet Watch for the new Pandora project that's going to come up, and citizen science is all a part of that. And you can get telescope time on anything from your own 3-inch to 8-inch for exoplanet stuff. AstroImage-J was in there too. Allison, that light curve that went up and then down, something in the back, something that may have come in across that we hadn't discovered before? You know, before you're on April 20th and 24th, your 22nd was your expected curve, but there was an increase in brightness and then a decrease. What do you, I mean, we're not going to guess, but what's your guess?
I mean, given it's like it was the same change in brightness both times, like it could be another planet. Like obviously the first we considered was that it's just a systematic error in our data. So we tried it with different comparison stars, but then we used the same comparison stars in like all three observations, but we got the one light curve on the 22nd and the two stranger light curves on the 20th and 24th. So we kind of thought that maybe it wasn't as much of an error and that maybe there is another like object in the system. Could be another planet, could be something else. We're not
A
really
super
sure.
Jupiter further out that would take 4 days to go around, indeed. Can I, unless, go ahead, but I'm going to ask you to close your slides because your video freezes. And if people want to ask you questions, I don't want to have you, when your audio comes through, but you're frozen.
Okay.
Thanks. Bill, you had a question?
Oh, no, I was just going to say another possible reason for that kind of curve is something that happened either to the star itself or like we saw with Betelgeuse, potentially some outflows from the star or gaseous, something in the gaseous disk around it.
Isn't Betelgeuse
that definitely could be a
a
possibility.
known variable, though?
So 2 years ago, we saw that there was a great diminishing of Betelgeuse luminosity, if you recall.
Yes.
And there's it seems like there's a couple of different theories about why, and I haven't seen that it got pinned down, but as an old star, it does have a lot of gaseous outflows, and perhaps that came between us and the star, and thus reducing the luminosity apparent to us.
I did say the name 3 times too.
Mm.
Other questions? I don't have anyone in the chat asking one. Comments even? Let me scroll through so I see if I have any hands up.
Yeah, Allison, I'll second that. Great job. That was a wonderful presentation. I really appreciate your thoughtful discussion on the error sources. That's incredibly important with data like this. So you really detailed that quite well, both with the plots of the light curves and how, you merged 5 data points into one with the error bars. So you did a great job even showing the error bars on the data points. So it was really clear, your discussion on the sources of error and the size of the error. So really great job on that. And that's so important in research, is to analyze the error.
Yeah.
And using that plane wave 24-inch at the Phillips Observatory is very familiar to us too. We have one here locally at our home observatory at the university.
Oh, cool.
That was a very good presentation. My dad formed this club like back in 1951, and he would have been thoroughly impressed with what you did. Thank you so much.
Charles Hammond's son, Bob.
No, thank you.
What are your next steps?
Well, I've been kind of talking with my mentor about maybe trying to get some more telescope time. It's tricky now just because we're getting into the summer and that's like thunderstorm season in Arizona. And then as for me personally, I'm going to college next year. And I hope to kind of try and do some astronomy stuff. I don't have like a major in it, but maybe a minor.
Where are you headed?
I'm going to Vanderbilt.
Nice.
Hi, Allison. I want to just say hello. I'm Scott. I arrived late here in Rochester and got hooked up to about a third of the way in of your program, and I'm very glad to be able to at least see some of it. Sorry, my camera is not on in the on the computer here, but I really, with the amount of their program I did see, my brain is full. So really enjoyed it, and I hope that we have the opportunity to cross paths again in the future, either by reading about works you have done, or maybe you'll be able to show up at a meeting. But thanks again.
Try the Night Sky Network too. There's also opportunities for telescope time through some resources they may suggest. Some are free even. Even amateurs can lend you time on their telescopes if they're willing to give them the time to set up the scope for you in advance, I've learned for some of these talks.
Yeah. I definitely have to get away from where I live because we have so much light pollution, you can barely see the stars.
Let's not compare notes.
Yeah, isn't that the truth? Allison, quick question with I didn't, I'll admit I wasn't following the calculations on on the size, the size of the exoplanets you were looking at. But, were you getting a calculation? Were you getting a sizing of the radius of the exoplanet from your calculations?
Yeah, we were able to get values. They're just like there's like a lot of error in them and stuff. Because we were only kind of able to do it precisely to like two significant figures. But yeah, we did get values for them.
I mean, were we talking Jupiter sized or anywhere near Jupiter sized?
Yeah, like two of them were like around the size of Jupiter, and then I think one of them was a little bit smaller.
Oh, nice, nice.
I wrote down the test objects of interest for you and the math, Chris, so you can practice and study at home.
Yeah, yeah. I'll do that, John. Thank you.
Hey,
That was
Allison.
Yeah, go ahead.
Hey, Allison. My name is Cindy. It was a great presentation. Thank you so much. And I'm so glad to see that your mentor was Don McCarthy and that you went to that camp, because before they do the camp for the students, they do 1 week for adults. So several years ago, I had gone to that camp, and it was so much fun, and learned so much. So glad to see that you were taking advantage of that. And best wishes to you at Vanderbilt.
Thank you. Yeah, it was definitely a fun experience. That was when I was right after sophomore year. I did that.
Cool.
She managed to get that done in less than 30 minutes, including question time. So I think we could stand to have a couple more questions. Although if you haven't, go look up Exoplanet Watch on the Night Sky Network on YouTube.
I think I'm like I get like their like newsletter. I forget it's a monthly.
Okay, well, there is a talk almost every month of the year, and Exoplanet Watch was one of them just most recently. If you look at their YouTube channel, you could find it. But Pandora is we have one of the principal investigators or scientists on that who gave us a talk on the Pandora mission that's scheduled to launch possibly this fall. Dr. Rob Zellum from NASA Goddard.
I could follow up on the planet size question. Your errors, your uncertainties were about 50%, maybe less than 50%, which I don't think is bad at all. What was it? What was a greater source of error? Was it the star radius from the literature, or so what was the relative size of the source of error from the delta from your curve?
It was definitely more the delta than the star radius.
Okay, so the star radius was fairly well certain. Okay.
Yeah,
but I don't think those are bad uncertainties at all.
No.
Oh, and for your benefit, we have 12 people online, and what do we have in the room now? Seven?
We have 7 counting myself.
Okay, so if you're keeping track, Allison, we had 12 plus 7, 19 total. for your talk.
Great.
Any
Anybody
final
else?
questions, or will Allison get back on with their life?
I would
You're
just
welcome.
offer to Allison that the 8A VSO has a fairly robust section on exoplanet observations, and they're keeping a database on amateur exoplanet observations in photometry.
I'm glad you brought that up. It's also the source for people who don't even have an AVSO membership can put up amateur data there through Exoplanet Watch and using the exotic software. I learned a lot.
Yeah, I
this
think we
past
have,
week.
I have like one like through my school, I think.
Hmm.
Like we have one that we can use. But I
You don't
also
even
like,
need a paid account. You can do it as a researcher.
yeah, I think also we've talked about uploading our results to Exofop. So I know like they're kind of compiling a lot of stuff too.
Yep. All that data helps the big telescopes, Keck, James Webb, shave off 15 minutes of observation time on either end, saves a lot of telescope money time.
All right.
Thank you, Allison, so much.
Thank you.
Give
Thank
her a
you.
little round.
Thank you. It was nice meeting you all.